Welcome to the third video of STEVAL-FCU001V1. Today we will see the configuration and the tuning for external ESC configuration. Here is the flight controller that is mounted on a typical racing drone. We can see the difference with the smaller drone that we have seen in other videos. So the main differences are the weight, first of all. So while the small one is below 100 gram, the racing one with external ESC can be 200, 300, 400 grams. And the key point is the motors used. So for the mini one is the DC motor, while for the big one we have the DC brushless. So here it is the configuration as we have seen with the DC motors for the mini drone, in which the motors are directly connected to the flight controller and also the one cell battery. While in the case of the external ESC, we have a battery that is going to the ESC where there is a BAC, or basically a DC-DC converter, and we have the 4 PWM. You can see also that is needed a small modification to the resistors connected on the flight controller that are bypassing the MOSFET in order not to burn the microcontroller on the ESC. You can see also on the racing drone that we have seen before. Here is the connector for the external LiPo battery, and the rating of the battery can vary depending on the capability of the ESC and the PDB. Here is the PDB, basically is a board where there is a DC-DC converter, and here the ESC. The ESC is taking power directly from the battery applied, while the flight controller unit is taking 5 volt from the PDB. Here is a typical LiPo battery for racing drones. In this case is 3S or 4S, and we can see the difference with the small one of the mini drone. Here also in the mini drone we may use the external remote, and here is the receiver of the remote. And we have the same kind of receiver also in this configuration with the ESC. I strongly recommend to use an external remote in the case of external ESC configuration, because the drone is much faster and need more precise control. Also the maximum distance of the BLE is just 15 meters, and it's not proper for outdoor use. See how to program the flight controller for the ESC configuration. Here I use an ST-Link that I connect to the flight controller unit in order to program and debug the firmware on the STM32. I use an ST-Link, but you can use also a other JTAG device or a nucleo board. And here I put a battery checker with a beeper on the LiPo battery. It's important to check always the voltage level of the battery, because if during the debugging phase you discharge it completely, you can damage permanently the LiPo battery. So let's open the firmware project of the flight controller unit. At first we need to go in a motor.h file, and here we can see, and also in other parts of the code, define for the motor ESC configuration or for the motor DC configuration. So here we uncomment the motor ESC configuration, and we see here that we will have a different range for the PWM value that is going from the flight controller unit to the ESC. And this is different from the one that we had in case of the DC motors. In fact, for the DC motors we just give the PWM to the MOSFET, while in case of the ESC we need to give a specific frequency, in this case is 400 Hz, and we are giving the minimum speed or the maximum speed varying the on time of the PWM from 1 to 2 milliseconds. So we can see that in case also of a signal with a on time less than 1 millisecond, we say that the ESC is disarmed, and depending on the ESC model they emit a certain beep sound of alarm for it, while when we pass this threshold the ESC is armed but with the motor stopped, and varying from 1.1 millisecond, but this value can vary from ESC to ESC to typically a maximum value of 2 milliseconds, we vary the speed from minimum to maximum value. So the value that we are going to change in the firmware and fine tune depending on the ESC is the minimum throttle value, and we are going to change the minimum and maximum PWM value, and the prescaler of the timer in order to change the frequency of the PWM from typically from 50 to 400 Hz. When we power the flight controller unit, this will be in a kind of a standby mode, in which the PWM is already generated and is sent to the ESC, so the ESC will be already in armed mode. But if we change the throttle on the remote, basically the PWM is not changing, so the motor are still in stop condition. So the sequence that we need to perform in order to power up the motor is at first to make the calibration of the sensor with the joysticks of the remote in that specific position, and then the next step will be to arm the motor. In this case, arm the motor means that when we will increment the throttle value on the remote, then the PWM will vary from 1 millisecond up to 2 milliseconds, and so the motor will spin. So let's at first the LED is blinking, then we run the sensor calibration, and we arm the motor. So now the LED will be in a fixed position. So in this condition, with the FCU and the ESC armed, we can increase the throttle, and we will see the motor that will spin. There are a few other parameters that we may need to fine-tune later. At first, the PID. So the PID may be quite different in case of the bigger drones with external ESC, and also the slope rate of the throttle versus the input, in this case is the GTHR variable that is coming from the remote. This slope can be quite different from the one used for a DC motor configuration with the mini drone. So we have seen all the basic modification and fine-tuning that we needed to do for the external ESC configuration for the flight controller unit firmware. As you see, we have done all the tests with the battery checker inserted in the battery and the propellers off. The next step will be to go outside in a wider space and with the propeller on to test the drone in flight condition and eventually make a fine-tuning of the PID and the remote con ratings.